Hi, everyone. Again, just to reiterate, really pleased that you've all shown up for your learning and that you've all started considering Jackson the Ladybug and his incredible voyage as he travels about on the inside of this bike tire. So, I gave you this example, wanted you to think about this example to notice some of the connections between A, K, C, and D and the physical features of the problem. What about the physical nature of the bike? And can you connect with things like amplitude, period, frequency, and horizontal axis? What do you notice here? Allie? Oh, yeah. Yeah, cool. Yeah. So I told you that this bike tire has a radius of 75 centimeters. It's a really big bike tire. Is that 75 going to show up in like a function if we created a function somewhere? How would it show up? Did you say it earlier? Yeah, this is going to be our amplitude, right? So the radius here, we can notice that that's equal to A. That's equal to the amplitude, the 75 centimeters. Cool. All right. How high would the horizontal axis be in this case? Yeah. But is it 75 high because the radius is 75? Would that be true of, say, a Ferris wheel? The horizontal axis also be the same as the radius? Lily, you're shaking your head. Why? Oh, okay. Well, it's. If you imagine that the Ferris wheel, like the London Eye, it's up in the air, and the bottom car is above the ground. Then no. So, what physical feature of this wheel would correspond with the horizontal axis? Also starts with AX. The axis is the same as the what part of the bike wheel? The axle. Yeah. So an axle. Oh, the little. I'll let Oscar answer that question for you. So this feature of the bike wheel here, however high it is, that gives us the difference between the average between the maximum and the minimum position. If we move that up and down, like you had, say the bike rider does a really cool wheelie, then Jackson would be going through the same periodic function but raised off of the ground. Cool, right? All right. So C here would be 75 as well. And then we know that it makes one revolution every 5 seconds. So how would we find K?
360 divided by 5.
360 divided by 5. That is 20, 40.
72.
72. Yeah. K equals 360 divided by 5. That gives us a K of 72. Whoa, that's a really fast periodic function. Great. Now, we made this graph, and this graph would be useful to us to solve these types of problems, like particularly the one with the cat. How could you use this this graph to solve this question about the cat without even creating the equation of a function? All right. So let's draw the cat. The cat is 30 centimeters tall. There we go. Here is the cat. It has a curly tail, some legs.
That's a really weird looking cat.
There we go. All right. Jackson's going to pass the cat at 62 seconds. Will Jackson be in danger or not in danger?
Not in danger.
How do you know this, Malcolm?
Because if we say 62 seconds is like just past half, he's still not in danger.
Are we ready to head over? I'm really confused.
Well, we're gonna drive past the cat, and the cat might try and swipe at Jackson. I didn't imagine what you just imagined, but now that I have,
I was picturing this.
yeah. So
Wait, you're still gonna hit the cat. Yeah. That's what I mean, like the bike tire, regardless of where the ladybug is, would hit the. And then the ladybug's gonna fall off because of the cat.
I clearly had some unconsidered implications to this situation, but I think we can agree that since 62 seconds is going to be, Josh told me it's 12.4 revolutions. So 12 revolutions is exactly 60 seconds. We know 0 and 60 are going to be the same. He's going to be down here. He will be 2 seconds into one of his revolutions. He's going to be nearly at the top. He's well safe. So we can clearly see that even without creating a function. Yeah. So that's how we know. We know by extend the function periodically.
You would accept that as an answer?
Extend the function periodically, and we'll see that he's 2 seconds into a cycle. The same height. He'll be at 2 seconds. That's plenty high enough.
You don't pronounce the T, there's no E after it.
No, it's clearly chat.
To avoid mischief.
No, the kids singing in French.
Oh my god.
Nobody's kids are like singing in French.
Wasn't it beautiful?
I was kind of cool.
Yeah.
I
All right.
was so confused.
But if I want to know, like the first 8 times, Jackson's going to be 140 centimeters above the ground. This is more of like a math teacher type question that I might ask. I don't really know the consequences of him being that high, but I don't have enough resolution here. Yeah, kind of needing to shout over people at this point. So watch that. No, it's Tuesday. So when is he over 140 centimeters? Well, we see that we get all 8 here, but I might want to find those more exactly. So see if we can find that. To do that, we need an equation. So let's find an equation for this situation.
So would you do 140 equals and then the equation?
Sorry?
Never mind.
Okay, yeah, so you can say, yeah, we'd use 140 equals. Yeah, that's right. Hold on one moment. More boisterous. All right, so this is a very like math teacher type question. It's the kind of thing you might see on tests. Let's see if we can solve it using an actual equation. So, we've already got our A, K, C, and D. If you recall, A was 75 centimeters, but we're just going to use 75 and know that the output of the function is in centimeters. K was equal to 72, and C was, by coincidence, actually 75. Not coincidence. Oftentimes when you have a wheel going around and your minimum is at 0, your C will be the amplitude. But if you have a Ferris wheel lifted up in the air, we're going to take a look at another example today where C and A are not the same thing. They're not always the same. Now, let's carry on. We need to find a D value. And the convenient thing about this question is it starts at a minimum. And I'll show you a trick. If you're starting at a minimum, you could use a cosine function. Cosine starts at the maximum. So you can have a D value of 0 and a negative A value. And you will start at the minimum. Because what happens if I have A is less than 0? What kind of transformation does that give me? Yeah, it's going to reflect in the x-axis. So rather than starting at the maximum, it will start at the minimum. So let's try that so that we can do this one quickly. So here we will go. So instead of A being 75, we will say f of x is a function that gives me his height, and it's equal to negative 75 cosine of 72x plus 75. All right. Now, that will be this function that we've just graphed. Now, this function that we graphed, we did it without an equation. We were very confident that, that would be the function based on the geometry of the wheel.
Where's the D value?
We don't need one because we used cosine. D is 0. Okay. You want to see it? Let's see it. So I'll show you this function that we've just created. It would look like this. First of all, whenever using Desmos for these, your first stop is flip that 2 degrees and then go ahead and punch this in. F of x is equal to negative 75 cosine of 72x and the bracket plus 75. And then you go ahead and change your scale so that it matches the scale I gave you over there. So we're going to want to see y values up to about 170. And then we want to see x values out to 60 because that's the first 60 seconds of his tour. Wait, no, we only looked at, we only need 20. 20 seconds is good. There we go. So there we have it. And that's the function that matches what we have in our graph. Notice that if we didn't use a negative 75, we would be starting at the top of our period. And what we could do if we wanted to have a d value here is we could say I want to start at the bottom. So I know that the period is 5. I want to shift that by half of the period. So I can either do plus or minus in here, 2.5. Minus 2.5 will do it. There you go. But this idea of using negative a values is such a neat trick that I wanted you to see an example of it. So there's a trick that you can use to start your function at a minimum if you want. You can start at negative cosine. If you want to start at the horizontal axis and go down, you could use negative sign, a negative a value for sine. That would be start at a value and go down. Okay. So we have our function. If we were working on like an assignment where we have access to Desmos, you could solve this in Desmos this way. Y is equal to 140, and then find the first 8 points. Boop, 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 and boop, boop. But we're not doing that. We're going to do it algebraically. Let's go algebraically. Yeah? Oh, was it frozen or something? What? Why? What I just did?
Yeah.
Took me how many seconds? 15 seconds? A lot of work. You and I got different ideas of what a lot of work means. Yeah?
It's actually a math question.
Okay.
Why are we using cos? Like, can you use sine or cos?
Yeah, we could use sine.
Okay.
Sine would necessarily have a d value.
Okay.
Because I could simplify this by not having a d value, I chose to go in this direction. Okay.
So sine needs a d value? Or?
No, in this case, sine will need a d value.
Okay.
Because, sorry? Oh, because if I use sine, and I'll build one with sine here, sure. I'm just going to go ahead and duplicate that, change this to sine, and then show you the transformation we need. It's going to be minus 1.25. It's going to be minus 1.25. So if this is sine, here I'm going to not show that for now. We're going to go back to a positive sign. Notice sine, it starts at the midpoint and goes up. That's like saying Jackson got on the wheel at the height of the axle.
So
Maybe he was on a bush and jumped on.
cos will start at the max or the min?
Cos starts at the max and goes down.
Okay.
Sine starts at the axis and goes up. So
And
if we make that negative, the maximum
start
starts
and
to
go
the middle,
down.
and that's why.
yeah, if we made this negative, it would still start at the midline and go down. There, see? So those are the tricks that you can use. If I wanted to insist on using sine here, the x value would be minus 1.25. There we go. How did I know that? I knew that because that was 1/4 of the period, and I want to shift this over by 1/4 of the period. You will only develop that awareness by a lot of practice. So let's get more practice by showing you how to do this algebraically. Let's go. Let's do this algebraically. We want to know when does f of x equal 140? Let's find out. So what we can do is plug this in. 140 equals negative 75 multiplied by cosine 72 of x for some value of x. We don't know that yet. Plus 75. Okay. Go ahead and get your inverse operations pen out. And we're going to simplify around, we're effectively trying to solve for x. So we want to peel away the layers of armor in inverse Bedmus order. So that's going to be addition and subtraction goes away first. And then we can have a new line there. This is 140 minus 75 gives us, what is that? 65. 65 equals negative 75 cosine of 72x. Our next inverse operation, divide by negative 75. So 65 divided by negative 75 happens to be close to a exact trigonometric ratio. So 65 over 75 will reduce to 13 over 15, but it's negative. And that's equal to cosine of 72x. Are people all right with me reducing that? Like you can see that reduces, you take out your factor 5, like it's instinct now, you do that by instinct. Good. Okay. So, and then now you take the inverse cosine of both sides. That's your inverse operation here. So cos inverse of this should be equal to 72 times x. So let's go ahead and find that. Oh, right, we need a calculator for that. My goodness. So 13 divided by 15 equals that, but we want the negative one. So there is negative 13 over 15. Now I'm ready to take the cosine inverse of that. And it tells me it happens at 150 degrees.
Wait, so sorry.
Huh? What's that?
So did you do cos negative 1?
Cos inverse.
Hold on, let me do that.
Yeah.
With the exact value like that.
You find the decimal 13.
Yeah, but before we get there, we have to do a bit of stuff, a bit of doing. Okay. There's a bit of doing before we get there, Oscar. Okay. Negative 60, eh? That's interesting. Your calculator is giving a different answer. So, negative 60. That's strange. We'll have to take a look at that in a second. So, this is what we do with this. We know that one possible solution is 150, and we want to look for other angles that also have a cosine of 150. So if we had, so there it helps to think about, if I have 150 degrees there, so that'd be 30 degrees would be my reference angle. What other angle also has a cosine of this number? Yeah?
Sorry, backtrack for a second.
Yeah.
Why don't you divide 150 by 72?
Because I'm going to get two solutions. So before I divide by 72, I want the two solutions. I'm going to split them up separately.
Oh, because then you can use those two solutions
to find the two values. Okay. If we look up here, visually we know we're looking for this value and that value. Two values. Right? Two values per period where he's at 140 centimeters. To find the two, you need to find the two angles that have the same cosine. If I told you, find me two angles that both have a cosine of negative 13 over 15, and you found one of them is 150 degrees, what's the other one?
30.
No. Because its cosine is negative. Remember, this is a negative number in here. So we're looking for another cosine that's negative, but it's the same as 150.
330?
No.
Oh, 150, sorry.
So we have 150. 150 happens to be 180 minus 30. What's the other one?
210?
Oh.
210 is correct.
Yeah.
So 150 or 210. are our solutions to these equations. We're going to split those into two equations. And let's look at that. Let's be very clear on why that is. And we can think about it with the unit circle, but you can also think about it with your parent function cosine graph. So let's go ahead and look at that. Your parent function cosine graph is absolutely something that can go onto your cheat sheet. We're going to want to see values of x up to 360. So let's do that. 360. There we go. And we have cosine of x. There it is. If I want to look for negative 13 over 15 equals y, oops, the equals ended up in the wrong place, equals y, there's my two solutions at 150 and 210. So by visualizing the cosine curve, that it starts at its maximum, goes down, goes underneath, and hits and comes back up to its maximum by 360, you can kind of imagine where it's going to have its two solutions. You can see them there. When you do cos inverse, that's what you're finding, is the x values, right? So that's connect to your parent function curve. So these are the 2 points where when 72 times x equals those angles, that's when he's at 140 centimeters.
Okay, so then you set those in for
Yeah. That's right. So now we're going to have 150 equals 72x, or 210 equals 72x. Okay? That's the solution to this here. And there are two solutions, and we want both of them. Okay? All right. So let's solve those. 150 divided by 72. We're going to need a calculator again, because that doesn't have many factors that cancel. Oops. 72 equals, so x is 2.08. Or we have 210 divided by 72. Oh, 2.992. Now, what we have found are the first 2 times that Jackson is 140 centimeters above the ground. How will we find the first 8? Just like right away. So work visually. I would suggest to understand the method. The method is, I just found this one. That's at 2.08, and this one was at 2.92. Okay, that's 2.92. That's 2.08. Just add 5 to that one to get that one. Just add 5 to that one to get that one. So the next ones will be at 7.08 and 7.92. The ones after that will be at 12.08 and 12.92. And then 17.08 and 17.92. Yes, Malcolm? Huh? No, I don't think I did. I think I'm recording. It's going. And sometimes that's good news, Malcolm, because it means I do it in period 3 anyway. Okay. So then I would just finish with a little list and say, therefore, Jackson is at 140 centimeters at 2.08, 2.92, 7.08, 7.92, 12.08, 12.92, and and 17.08 and 17.92 seconds. There. That's how you do those types of problems. Oh my goodness. It took a lot longer to talk about Jackson than I thought it would. All right, so then we get to the lesson. Yeah. So I know. It's not very good. So for now, we're going to wrap it up for this example. Thanks for showing up for your learning. Bye for now.